Hi friends, hope you are all doing fine. So today I'm going to start one more math question bank set, and here I'm going to discuss 5 questions and then we are going to solve these problems. Now these questions are very useful in testing some basic concepts of mathematics. So let's begin. I'm Dr. Ganguly. Now let's look at the first question, which essentially asks you to integrate this problem or integrate this function ex sin x, and you are asked to actually integrate this without using integration by parts. Now this is an integral which is often solved by integration by parts, and that's something which we have also done in a previous question bank. So just to review this question, I will give you the solution here in terms of integration by part. This we have done in math question bank 1. So essentially you use the integration by part formula here, and then after a few steps what happens is that this integral again comes back on this particular side, and so we get I is this particular function which I have shown in green. Now if you want to take a look at how I have worked this out, you can take a look at math question bank 1. But in this particular problem we are asking the student to solve this using some different method. Now this kind of questioning is very useful if you have asked this integral before to some student, he or she may have done it using integration by part, then you can ask this question now. So here one of the things I'm going to demonstrate to you is how this can be done using the theory of complex numbers. So there is a very important formula, and this formula is e to the power ix is cos x plus I sin x. So this formula links the exponential function to the sinusoidal functions. And so if we use this formula, we can immediately write ex sin x dx as the imaginary part of ex into eix dx. So you can clearly see that in this function, the imaginary part of eix is simply going to be sin x. So I have replaced sin x by that. And by writing it in this form, I can immediately write it as e to the power I plus 1 x dx. And you know the integral of this simple exponential function can be written as e to the power 1 plus ix by 1 plus I. And there is of course the integration constant c. Now we have to find the imaginary part of this particular quantity. So this becomes more of a problem in complex numbers. So let us try to take this function and try to reduce it to a simpler form. So what we do is we first try to fix this 1 plus I below. So to do that, I can multiply the numerator and denominator both by 1 minus I. So what happens in the denominator, I get the 1 minus I squared term. On top, I have 1 minus I. And so now this I square, of course, you remember is negative 1. So this becomes 2. So I have 1 minus I by 2 and e to the power 1 plus ix. Now what I do is I expand this into e to the power x and e to the power ix, and so e to the power ix I know is this here which I have given in purple, and so I get this equation here. I further expand all the terms out to get this here. So essentially what I have done is multiplied this whole thing by 1 and then multiplied this whole thing by negative I. So it's given me this particular function here. So ex by 2 into cos x plus I sin x minus I cos x and minus I square sin x. That's what we get here. So let's now simplify this further in our next slide. So I again wrote the same equation here, and now what I have done, I have replaced I square by negative 1. So I have got this plus sin x term here. Now in this particular function, what I can do is I can take all the real terms to one side and then I can take all the imaginary terms to one side. So this simply means that these are the terms which are the coefficient of I here. Now then what I can do is I can take a look at this and I will immediately realize that the imaginary part of this function is going to be ex by 2 sin x minus cos x. So essentially that is the integral here, which we have also obtained previously using integration by part, and I add this c here. That's the constant we need to add whenever we have an indefinite integral. So this is a very good problem by which you can check out the knowledge of the student in terms of basic things about complex numbers. and you can also introduce the importance of this particular relationship. Now let's try to look at some very elementary differential equations which can often be used to test the knowledge of students. So let's start with this very simple differential equation, d2x by dt2 minus x equal to 0, and there are two initial conditions here, that is x at 0 is 1 and dx by dt at 0 is 2. Now these are problems which are quite ubiquitous in various systems, and what happens is that when you find the solution x, which is a function of t, that is often known as the response of this particular system. This is, you can think of it as a dynamical system. And sometimes these problems are known as initial value problems also, because what's happening is that the initial conditions are being prescribed here. So this is different from boundary value problems. So let us try to solve this equation, and to solve this equation the standard procedure is to make a substitution. Xt is e to the power st, and if we then take the derivative and the second derivative, we are going to see that the second derivative is actually the exponential function again, and it's scaled by this s square. Now the reason we take this exponential here is that what happens is that you get a very nice form of this equation, and you will get this equation which is known as the characteristic equation. So what I've done is substituted this derivative here and substituted x here, and I get this equation here. Now looking at this equation, I clearly know that e to the power st is not going to be 0. So s square minus 1 is going to be 0, and therefore s is equal to plus minus 1. So there are essentially two roots here. So I have two solutions. The first solution could be e to the power t if I put s is 1 here, and the second solution is e to the power minus t if I put minus 1 here. So if I add these two solutions and I put two constants, I get xt is c1 et plus c2 e minus t. This is typically known as the general solution of this equation. But you will see in the general solution, the initial conditions never came in. So let's try to do that in the next slide. So now what I do is I take this solution and I substitute the initial condition. So if I put t is 0, I get x0 is c1 1 plus c2 1 is 1. Nice thing about exponential function is that when t is 0, they simply become 1 here. And now I take the dx by dt here, and so again I calculate the derivative here. Of course, what will happen, a negative term will come here because e to the power minus t when differentiated will throw a minus 1. So I get dx by dt. I put dx by dt at 0 is this value, and remember this is given as 2. Now I have these two equations, very simple ones, which I have given in pink. These are simultaneous equations, so I can solve for c1 and c2. If we were to add these two equations, I would get 2c1 is 3. If I was to subtract these two equations, I would get 2c1, 2c2 equals minus 1. So 1 minus 2 is minus 1. So from this I get c1 is 3 by 2 and c2 is minus half. I put these into the general equation here, and so I get the solution. Xt is 3 by 2 et minus half e minus t. So this is actually the solution of this differential equation in red once the initial conditions have been put into the problem. Now the nice thing about actually getting a solution in this form, which is using numbers, is that we can very easily plot it. So here I have plotted xt with respect to time in Excel, and of course you can see that it's starting from 1 at t is 0, and then it is growing. So this is an exponential solution. Now this kind of solution is typically the response of the system. It's a very important problem in dynamics because we often try to find the response of the system in dynamics. Now of course equations may be more complex, but you are getting the basic idea that in any case, if you solve the differential equation for the system, you are able to get the response for the system. That's something which is very important. Now let's do a trick on this problem, and what we are going to do is pose the same problem to the student, but tell them that they cannot use exponential approximation. They have to solve this problem using a trigonometric solution. So this is like a curved ball or a googly thrown at the student, and many students will get extremely perturbed when you ask this question, but of course they will have to do it. So what I'm going to do is I'm going to now take xt in terms of sine and cosine, and I'm going to assume that xt is a sine st plus b cos st. I immediately differentiate it to get dx by dt, and I again differentiate it to get the second derivative of x with respect to t. So remember, sine, if you differentiate it, you get cos st, and there's an s here. You again differentiate it, you get sine st, and now this becomes negative s square. So the derivative of sine is cos, the derivative of cos is negative sine, and similarly you get this equation here. Now let's put all these derivative terms into the actual differential equation, and we get this equation out here. And then what I do is I collect different parts together. So I take a sine st term, I collect the 1 plus s squared term, I take the b cos st term, I collect 1 plus s squared term, and so I'm able to write this equation here. Now looking at this equation, I of course don't want this a sine st plus b cos st to be 0, because that would mean that there is essentially no response in the system. That's a trivial solution. So I say 1 plus s square is 0, and immediately I get s is plus minus I. So remember, I is of course root of negative 1. Now, therefore, I'm going to get two solutions of this equation. x1t is a sine it plus b cos it. So remember here that s was I, so I made that substitution. The second substitution is negative I, and so that gives me minus a sine it plus b cos it. So remember, cos of the negative number simply throws that number back to you, but sine actually keeps the negative there. So that's something we know from the definitions of the function sine and cosine. So now I can get the solution by simply adding these two solutions and putting a constant. So let's do that. So if we do that, we were to get this here. So if the solution was cx1 plus dx2, I put in the x1 and x2 from the previous equations, I get this solution. And then I can actually absorb the different constants and write it in terms of different constants e and f. So xt would be e sine it plus f cos it. So you can see here that if I would take the coefficients of sine, for example, I would get Ca minus dA, and so all I'm doing is I'm declaring that as a new constant E, and similarly I'm doing that for F. So this is the solution now, and interestingly I have got this I here. So you may stop at this point, or you may want the student to simplify this further, and that's what we will do in our next slide. And for that we just recapitulate the complex exponential formula. So essentially we have EIX is cos x plus I sin x. I can immediately write E negative Ix is cos x minus I sin x, and therefore if I were to add these two, I would get cos x is this particular function here, and I would get sin x is this particular function here if I was going to subtract these two equations. So remember at all times that cos x and sin x are related to the exponentials using this particular formula. This essentially lets you go from the trigonometric space to the exponential space back and forth all the time. That's the thing we are trying to test in this particular problem. So let's start with this problem now. So we take this particular solution which we obtained. This is the general solution, and we put the initial conditions here. So x0 would simply be f is 1, because that's the sine t term would be 0 here. We take the derivative, we substitute for the derivative, and we get this equation here. So if we were to do that, we would get that IE equals 2, and therefore E is 2 by I, and remember I 1 by I is negative I, so this is minus 2I. I put it in the solution, I get this as the solution. Now I can use the formulas I showed in the previous slide, and I can expand the sine and cosine out. Now remember, sine x expansion I discussed in the previous slide. So if I was to get sine of it, I would essentially have e I it, and here again an iit. So this I have written in this manner. So it's a very interesting thing that iit is coming in this particular solution. Now, of course, you know that I square is negative 1. So both these terms involving I into I simply become minus 1, and the terms involving minus I become plus 1. So that's what you get. The two i's cancel out here. So I get minus e to the power minus t minus et plus this term here, and then I further simplify it and I get this equation here. Now, of course, we can immediately write it in this form here, which you will recall is the solution I obtained previously. So even while assuming a trigonometric solution through some manipulation and complex numbers, I was able to get back the exponential solution for this particular problem. Now, many people don't go about doing these things, but it's an interesting exercise in math which you can use to check out the student's capability in terms of complex numbers and basic calculus. Now let's turn to another differential equation where all I have done is I have flipped the sign. So in the previous equation there was a negative here, and now I'm taking a plus here. Now many of you who are from the dynamics background know that this is a very simple version of a spring mass system, and therefore it's a very important problem as far as dynamics is concerned. The initial conditions are exactly the same, and in the first question we are asked to find the exponential solution. Now many people look at this problem and they immediately go with the trigonometric solution, but what I'm going to do is I'm going to first ask the exponential solution, then I'm going to ask the trigonometric solution in the second part. So let's do that. Exponential solution is very easy to differentiate. So I start with xt, I get dx by dt, I get the second derivative, I put it all in the differential equation, I get s square plus 1 est equal to 0. I know est is not 0, so s square plus 1 is 0, so I get s is plus minus I. So there are two solutions. One solution is e to the power it, second solution is e to the power minus it. I combine these and so I get this as my solution, and of course now I have ended up getting the I value in the solution here. Now at this point this is a general solution. I have not included any boundary conditions, so certainly the general solution of even a very simple spring mass system can be written in this particular form. Now at this point you can stop, or I would say preferably you ask the student to continue further and simplify this. So to simplify this, let us first take this and include the boundary or the initial conditions here. So which I have done that. So x0 would simply mean that you put 0 in the time here, and so you get c1 plus c2 is 1. And then you take the derivative here. In the derivative, the I comes out of this particular exponential. And then what you do is you put t 0, and so you get this as the solution. Now what you do is you try to solve these two simultaneous equations. So one way to do it is to multiply the first equation by I, keep the second one the same, and then we can play around with these two equations. So let us first add these equations and then subtract these equations, and so what you are going to end up is C1 is 1 by 2 minus I and C2 is 1 by 2 plus I. Now in all these cases always remember that I square is negative 1, and of course 1 by I is negative I. So you can show these very easily. So you can write this general solution in this form here, or I should say rather, after including the initial conditions, the solution becomes this. Now you can of course further simplify it by using the relationship between the exponentials and the sine and cosine. So let's do that in this slide. So I take this here, I use this expression EIT is cos t plus I sine t, and I substitute it throughout this particular equation. So I have basically brought in the EIT here, and I have brought in the E minus IT here. And so after this, what I can do is I can take cos of t and bring all the coefficients of cos of t. So it will be half minus I and half plus I. So I put all these together. I take the I sine t term and I again bring half minus I, and I bring minus half minus I here. I get this term here. Now in this term the half plus half becomes 1. The minus I cancel, so it's simply cos t. In this case, the half minus half cancels. I get negative 2i, so I get this here. But there are two i's here. I into I is I square, that's minus 1. So I end up with xt is cos t plus 2 sin t, which is exactly the solution you would expect in this case. Let's plot this solution. So again, this is the solution here, and this is of course the response of this particular system. And you can see this is a response which is in terms of the trigonometric function. So that's the difference going from plus to minus did here. The initial conditions were exactly the same. So I simply have changed the particular fact that the second term involving x was positive in this case, and the previous case it was negative. Now finally question number 5 is the last question here, and in this case you give this differential equation with plus, but let the student assume a trigonometric solution. Now this is the natural choice, of course, in this problem, because most people who are familiar with simple harmonic motion, with spring mass systems and so on, will naturally select the trigonometric solution. So that's the advantage of having a solution which is already in a form which you expect. So in this case, if you choose x of t, differentiate it again, put it back in the differential equation here, you will get essentially that s will be plus minus 1. So you immediately get two solutions. The first is a sine t plus b cos t, and the second is minus a sine t plus b cos t. So essentially I have substituted s is 1 here, and then I have substituted s is minus 1 here. And always remember, cos of minus t is simply cos t, but sine of minus t is minus sine t. So that gave me these two solutions. Now, of course, I can take these two solutions and I can put some constants here, c and d. And then if I put these particular solutions back here, I can combine the terms involving sine and cos, and I end up with the general solution, which is xt is e sine t plus f cos t. Now we are ready to actually check this equation out in terms of the initial condition. So let's do that. Let's put t is 0. If we put t is 0, of course the e term vanishes because sine t is 0, and of course we get f, and f will be 1. And in the second case we take the derivative, so e sine t simply becomes e cos t, and f cos t becomes minus f sine t. Now we put t is 0, so of course what will happen, that only e will survive if we put t is 0, because sine t is 0, and so I get e equal to 2, and I get the solution immediately as xt is cos t plus 2 sine t. So these are some very simple examples, but you will be surprised as to how many students are not able to solve these particular equations. And in many situations, what happens in the different interview type of settings is that if a student is not able to solve a simple equation, that comes across more negatively, because if they are not able to do simple problems, then it's unlikely they are going to be able to do more complex problems. So one of the tactics, if you are in an interview panel and if you are trying to ask questions, is not to ask very difficult questions, because generally the student may not be able to answer the very difficult question, and that's okay. But if a student is not able to answer simple questions, not able to handle the pressure of the interview panel while he's answering, then it becomes somewhat difficult to take that student for college admission or for a STEM job interview situation. So before I conclude, I'll just give you the famous formulas here. So these formulas are extremely important. So remember always that Eix is cos x plus I sin x, and therefore E minus Ix is cos x minus I sin x, and through these two formulas we can essentially obtain this relationship between the trigonometric space and the exponential space. So this actually makes many integration problems much more amenable in terms of solution. So whenever you encounter integrals which are involving exponentials and cosine or sine, you can think about turning the entire problem into an exponential problem. So in my next question bank, I'm going to discuss some more difficult integrals which can be solved using such method, which were actually given out in examinations of the MIT and the IITs and other top institutions. So I'll stop this video now. Again, look at the videos on the end screen for more knowledge about topics. And certainly, if you have not been checking out my math question banks, do check out the question banks, because these will certainly help you improve your general knowledge of mathematics as well as make you a better person down the road.